Hello, in this video I want to show you how to extract molecular orbitals from Gaussian calculation. You need this, for instance, when you are working with UV-VIS absorption calculation, because sometimes you get interested in that you see a band in the spectrum and you want to know which orbitals are involved, from which orbitals to which orbitals this electronic excitation which you observe in the spectrum goes. So for that reason I have calculation of the UV-VIS spectrum already done. We see the output here in a log file, and I'm interested in the excitation energies and oscillator strength. This is the part of the calculation which I'm interested in. We see that there is excited state 1. It's at 416.8 nanometers, which means that if the calculation is correct, the molecule will probably have a yellow color, because this is the only thing which absorbs in the visible light region, which means that the blue light gets absorbed and what you get as an inverse color is yellow. The F value is 0.76, so the color should be very intense and the intensity of this absorption band is big. And what is interesting for us is that it goes from the orbital 62 to the orbital 63. So these two orbitals are the one which we want to visualize to know from where to where the electron goes. To do so, we first need to make a formatted checkpoint file. We do it by a form check command, and we apply this one on the checkpoint file, not onto the log file, but on the checkpoint file. What this form check command does is that it creates a more universal checkpoint file which is readable by different versions of Gaussian and also by some third-party softwares. Now we have the formatted checkpoint file, and from this formatted checkpoint file we want to extract the orbitals involved in this transition. We do this by a cube-gen command, and we use orbitals 62 and 63. To explain the whole command, we are using 5 threads. These are the molecular orbitals which we are interested in, for which we want to generate the cubes, and we are using this formatted checkpoint file as the input and this .cube file as the output. Now let's hit enter. As you see, it will use up to 5 threads. The downside of this command is that it takes some time. It's not the super quick command, for instance, as the form check command, but it will do the trick. So in the meanwhile, I can tell you a little bit more what you can do with this cube-gen. This one is from the official Gaussian site. The link will be in the description of this video. And what you can do is extract some molecular orbitals. You can also extract a density, for instance, the overall density of the molecule, which means the electron density, and you have much more variables which you can apply for and the information which you can extract by this command. For now, let's see how is the command progressing. It takes quite long. What we will do after we will extract these orbitals by this command is that we will open it in VMD software. This is a visualization software. So now it's done. Plus, we see here this cube file, and now we will open it in VMD. So VMD it is, and file new molecule, browse, and now we have the cube file. We see that it loaded and it recognized what is going on. We can even see here that we see orbital 62 and 63. We are interested in both. Click load. And now we have the molecule loaded in VMD. The downside is that it looks ugly at the moment, so let's lit it up a bit. I don't like this arrow, so X is off. I like rather graphics, colors, display, background white, because then you can easily extract it to supporting information. Then now everything looks a bit grayish. For that reason I turn off the depth cooling, and now you see some tiny lines. This is not what we want, so we go for graphics representations, and here drawing method we will switch to licorice. We'll increase the number of the resolution, I like 30, and bond radius to 0.2. Now the molecule looks somewhat reasonable, but we are not interested in the molecule itself, we are interested in what happens to the electrons around the structure. So for that reason we will create yet another representation by create rep, and then we switch from licorice to isosurface. In the isosurface, we are interested just for isosurface and draw method solid surface. Now it looks weird, that's because the ISO value is set at 0. We will set it to 0.015, and now we see some nice electron density. We see some nice orbital. If we set it to high number, let's say 0.3, the orbital gets smaller. If we set it to 0.01, the orbital gets bigger. I like 0.015. And now coloring method, switch to color ID, blue, it's okay. I want to use the orbital 62, the blue color, because I'm used to use the blue color for the base orbital, and I like to have it transparent. Once more, the transparency looks a bit awkward. How we will fix it is that we go for display, render mode, GLSL. Now it looks reasonable. We create yet another representation, change the color to red. We will use this one for the orbital 63. And now we can already observe that the electron gets excited from the blue orbital to the red one. And we see from where to where the electron density shifts during this excitation. This is it for this video. I hope that you have learned what you were looking for and that you will apply it for good use. Okay, thank you for watching. Have a nice day.